and it's long. I guess we're going to print it and put it somewhere. Again, this is more or less a social experiment. We found out that there is no better way to get people attention than just say that there is a challenge. And it's wonderful because you have to give no prize, no nothing. Just say, you know, you should win. It's like, yeah! Okay, perhaps we can get started. So let me just quickly remind you what we saw yesterday. So yesterday was meant to be like a warm-up. We didn't really see any particularly modern or new idea in machine learning. We kind of went over classical things such as logistic regression or support vector machines, perhaps in a slightly different way. So the first class was basically slowly going through the main concepts in statistical learning theory. So it's basically a setting. So it's basically a setting where we do assume the data to come from some probabilistic model, and then set up things, set up the whole problem in a probabilistic scenario. Okay. I won't say many things about that because it's more or less standard. I really just went over, tried to pinpoint some of the aspects, such as, for example, the idea that data might be high dimensional but lying on some low dimensional structure, the role of loss functions, what is the expected risk, what is the empirical risk, overfitting, and so on and so forth. The second class was really started to jump into algorithm, which is the main theme of this course. And basically what we did is just that we reviewed logistic regression and SVM. And the basic idea was to try to show you how once you have logistic regression in mind, and the idea of solving logistic regression through a simple gradient descent technique, you can somewhat extend this idea by going from gradients to this notion of subgradient that I introduced in a very informal way, and treat support vector machines pretty much in the same way. Okay? That kind of is a new way of looking at support vector machines. In my view, is much simpler, and while it loses a few things, it retains some of the main aspects. So somebody asked me, support vector machines is probably one of the most popular algorithm. So somebody asked, okay, it seems simpler than the usual derivation. Do I lose anything? Well, in fact, so the thing that with respect to the usual presentation of support vector machines, you lose the whole historical perspective. Things like the margin, the geometric story, separable, non-separable. That's kind of interesting in its own right to hear it once. I'm not sure that at this point it really is needed to understand how to use support vector machine. It's just one view with its own problem and its own nice thing. It's pedagogic to some extent, but has problem on other perspective. The other thing that you lose is this whole perspective in which you use Wolf duality and go through optimality conditions, so-called Kuhn-Tucker condition, Lagrangian duality, and so on and so forth. The way I see that, you know, there are two things. Okay, on the one hand, you can think of it as if you, as I was saying, when you invert a matrix in MATLAB or whatever routine you use, you don't ask what kind of algorithm that is using. Okay, and so similarly here, do we really need to know how to solve a quadratic programming problem or even get there? I'm not sure. Okay, so in some sense, yes, it's a technical fact. If you care about it, if you want to put your hand in it, you can go and dig your hand. But I gave you an alternative, which is very simple. The pros and cons of using some gradient versus quadratic programming are that in quadratic programming, you really exploit sparsity, potential sparsity, this idea of super vectors. So in some sense, you enforce coefficients to be 0. Okay? So if really the number of supervectors is small, you can have a big computational gain. But if the number of supervectors is not so small, and if you're in very high dimensions, typically first-order methods turn out to be more efficient, essentially because they're simple and they only require matrix vector multiplications. So in some sense, the idea of using first-order methods is becoming more and more popular, while things such as quadratic programming techniques to solve SVM sometimes are non-preferable when you really don't have a lot of supervectors, which often happen in high dimension. Okay? And then yesterday we started from linear models, and then we saw how we can use some linear features to go to nonlinear models, keeping the computation just the same, or we can use kernels to really get into something in the world of non-parametrics and still keeping computation that with up to some update are essentially the same. So what we want to do today is move on and look at different regularization principles, okay? While I was coming here, I was thinking that a few of the questions that I got yesterday are, okay, so you gave me a list of things. Should I use this or that? Should I do this or that, okay? This is not exactly what we're doing here, okay? One thing we're doing here is giving you principles and ideas so that you can understand how, not only how to use algorithms, but how to also develop algorithms, okay? So to do that, you have to know what are the different ideas that you can use to build learning algorithms, okay? So we try to do both things. I'm trying to show you algorithms and tell you when they work and how they work, but we also try to think what are the different ideas behind these algorithms, so that if tomorrow you need an algorithm, maybe you have to change it, maybe you have to develop a new one. And I would like you to know enough to at least get an idea of what are the different ingredients at the high level to put together learning algorithms. And if you have to say in one word what was the main idea in developing learning algorithm yesterday, what would it be? So the whole problem was trying to solve something like this. We stick to linear models for a while, and we say, oh, this is what we would like to solve, but we cannot, because we don't have the distribution and just the data. So what do? We said rather than the expected risk, we could look at what? And then we said, maybe it's not a good idea. Why? One word. Overfitting. And then we say, regularize. How? How did we regularize? We took the empirical risk and we added a penalty, okay? And then we spend most of the day just thinking of how you solve the optimization problem just with gradient descent or subgradient descent, okay? And as I mentioned several times, this is by far the most popular way, essentially because we took one penalty, the L2 norm, okay? But you could take other penalty and you can just add them and keep on going. So today we're still going to stick pretty much to the L2 norm, but we're going to do regularization in a different way, which is not by penalization. And in the end of the day, we're trying to try to compare and see if we learn something and if we can compare to what we did yesterday. Before doing that, we're actually going to entertain ourselves thinking a bit about least squares. So again, yesterday what we did was starting from something like this and saying, whenever you have a problem like this, you also have an optimization problem to solve that depends on the considered loss function. And we consider two cases, the logistic loss, the SVM. In both cases, if you remember, we used an expression like this. Notice that here, this is the functional that is regularized, okay? So I call E hat lambda the functional, which is the empirical risk plus the norm. And so this is the case, strictly speaking, for the logistic loss. You get something similar, replacing the gradient with something slightly different for SVM. Okay? Again, aside from the technicalities, like the idea of what is a subgradient, why does it work, you should appreciate from a practical perspective. So my idea was, if you know math enough, you can look at what I explained yesterday, you can fill in the gaps, just learning the first 2 pages of any books in convex analysis, and do the math yourself. If you don't like that part, you should appreciate just how simple the algorithms are. You can just try, implement them, and use them, because there's not much more than what I showed yesterday. It's literally like 3 lines of code. And both algorithms were basically this one line plus computation of this gradient. So what we want to start to do today is quickly go over square laws. Okay, this is the one left from yesterday that you already saw in the lab, and then generalize this, looking at different things. The square laws is particularly nice. Yesterday I asked you quickly if you know how to prove this. Did you try? Anybody tried? Yeah? No? Yeah? Well, you cannot. And you're too close to her. Yeah. How do you do that? Yeah. So what he said is y is plus or minus 1. So when you take y square, you always get 1. Okay? Which basically means that if there are tons of ways of doing this, but think of, for example, and also, you know, if you take 1 over y, that's also equal to y. Okay? Because it's just 1 or minus 1. So there are many ways of doing it. One way is basically if you take y here and you factorize it out, you get the 1 here. You get 1 over y here, but that's equal to y. And then you get a y square when you take it out of the parentheses. But y square is always equal to 1. Okay? So this should be a perfect way to wake up in the morning, right? You just why? Okay? But it's really simple. So you take y, you factorize it out, and you see what happens, okay? You got the 1 over y and a y square, and they do what they're supposed to do. Okay, what we want to do today is actually look at this functional if we plug in the square laws, okay? Again, this is pretty basic, and how many of you already saw this? All right, so remember that this is just empirical risk, okay? So it's a sum of terms. If you put the square laws, you can view that as entries of a vector, okay? Which vector? The vector looks like this. You take the data and you stack them into a matrix, okay? The input data are going to be rows of a matrix. So the size of the matrix is n rows, 1 per example, and d columns, 1 per variable. What you do is that you also do the same with y, okay? You take all the y's and you stack them on top of each other, and you get a vector of size n. Then you get w is size d, and now what you do is that you take these differences, and this is just the usual Euclidean norm. So you can, if you write it down as a sum, if you just take the norm and write it down in components or the sum of the square, you just get the usual least squares. Okay? That makes sense? So we're not going to do that. What we're going to do is just to take this, plug it in here, and try to solve it. Okay? So if you plug this in here, how is the functional we get? Well, it's easy to convince yourself that this is convex, okay? It might have a flat region if the matrix is not invertible, but, you know, side comment. But you add the strongly convex term, so this is really a strongly convex functional, so it has a unique minimizer, so we're happy. Also, this is smooth, and this is smooth. Okay, so you can just take gradients. So it's going to make our life easy. More than that, if you take x squared, what is the derivative? It's just 2x, okay? So that's the reason why we love squares and we put them everywhere. Because when you have a square, you get something linear. And when you do it twice, you get a linear equation. And life is beautiful. So if you take this square laws here and this term here, there are tons of ways you can do this calculation. You can do by components, you can introduce directional derivative, do the way you like it. You get that the gradient is equal to this quantity. It's twice divided by n, x hat transpose, blah, 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 plus twice lambda w, okay? You factorize w and you take y on the other side, and then this is the linear equation you get. Unlike the logistic loss function, where the optimality condition would not immediately give us an equation, here you really get just a linear equation. And really this happens because here you have square and square, whereas in logistic you have a mess and a square, okay? So here we could, but not need to go to gradient descent. In fact, we can just look at this linear system and try to solve it. What is the size of this linear system? How big is that matrix? There are two options, n or d. Okay? How big is this vector? D. So this matrix better be d by d, otherwise I made a mess. Okay? So basically, what are the computations that you need to do to solve this problem? Let's list them all. What are all the operations you need to do? Well, starting reading from the right, you have to take y and multiply by this guy. What's the cost of that? Again, this is fantastic after cappuccino too. So this is long n, this is nd, we take the transpose, so it's dn. It means that you have to multiply, how much is this? Psst. How much is it? nd, right? You have just a bunch of, you have a vector of size n here, you have several vectors of size n, computing an inner product between a vector of size n and another vector of size n costs you n. It's just n multiplications. But here you have d of them. So you have this n operation d times. Okay? It's useful to do this kind of stuff because you get the vague feeling of what is the cost of stuff. And we basically just have vector or matrix multiplication, and then there are basically two operations you have to remember. Okay? So here you have a matrix multiplication. How much is the cost of that? So this is nd, this is dn. So again, it means that you are multiplying vectors of size n, but how many of them? N times d squared, because you have d here, you have d here, and you have to multiply them all. And each time you do that, it's going to cost you n. So this is exactly nd squared. Okay? Sorry. Yes, nd squared. How much is the cost? Then we computed all the building blocks of the linear system. Now we have to solve the linear system in some way. And there are tons of ways of doing it. This is actually a nice matrix to define a linear system. Why? How is this matrix? Is it a general matrix? By no means, right? It is, and it is symmetric and at least positive semi-definite, okay? Which means that the eigenvalue might be 0, but they're positive, okay? They're never negative, sorry. So there are tons of ways of doing it. Cholesky decomposition or Cholesky decomposition, I never know what's the right pronunciation, is like one method of choice, but there are several others. So the cost of doing this is roughly nd squared to solve this and d cube, okay? Nd squared is the biggest cost in forming the elements, okay? Nd is the second order, and then you have this. And here you can see which of these two terms is dominating in this computation. So typically this is a good idea if n is much smaller than d, okay? Because in this case, this dominates a bit. Sorry, yes. Well, not true, sorry. This is depending on the size of n or d squared, or n or d, this term or this one is going to be dominating, okay? Now, as we asked the other time, suppose that now you have 10 points, but you have millions of dimensions, for example. 10 points maybe are a bit little, but you know, n is much smaller than d. Okay? So the natural question we asked yesterday is, can we rewrite the algorithm in such a way that the complexity will be led by n rather than d? Okay? So what we would like to do is to, in some sense, rewrite this in such a way that n and d swap. Okay? We would like to have dn squared and n cubed here, ideally. Yesterday we did something like this at some point, right? We took the linear model and we tried to swap the role of x and d. How did we do the n and d? How did we do that? What is the keyword here? Kernel was coming a bit later, but before that we did what? We didn't prove. We stated a little theorem that shows that you can swap and go from W to C, okay? And we called that a representer theorem. It's like a baby version of a representer theorem. It's without kernels, but in fact kernels, it will be just the same, okay? So we showed that W is not, so W is a vector of size D, okay? But we said it's not any vector of size D. The one W that solved this problem is actually a linear combination of what? Of the xi's, which are themselves vector of size D, okay? And they're the one we want to combine. This is exactly what's written here. So we hope that we can do again what we did yesterday. We can replace W with, if you want, if you write here, you see this X transpose, you can put it out of the sum. So really we are saying that W is equal to the sum of Xi Ci. This is just a way to write it when you evaluate the function. So you take W transpose X, okay? So if we can do this, we're in good shape because we could potentially replace W with C, and C is much smaller, and maybe things are going to be nice in our life. In the case of least squares, we don't prove it, but if you stare at the equation long enough, you can convince yourself it's true. And proving it is, again, basically one line. Look at this equation and just see what I did. So this is the one we introduced 30 seconds ago. What did I do here? I took this X transpose, okay? I moved it in front of the parenthesis, but then I have to be careful because otherwise the dimension gets screwed up. And so what I did here is that I swap, okay? There are two questions here. What did I achieve and how do you prove it, okay? Let's kill how do you prove it first. If you take the SVD of X, so remember that this means just that you're going to take X and write it this way, where where both this and this are orthogonal, and this is just a diagonal matrix, okay? And if you take the transpose, you just have to swap the order of U and V. So basically, one way to prove this equation is just to replace X hat with the SVD, and X hat transpose, again, with the expression of the SVD, and just check that they're true, okay? So this is, the fancy way of saying is that you use a little bit of spectral calculus, and you do it in one line. But literally, you just have to take this, plug it in here, take the expression for the transpose, plug it in there, and you just check that it's true, okay? There's nothing more. Let's go to the interesting part. What did we achieve? Well, so remember, X hat is ND. So this guy is going to be DN, okay? Which already hinted the fact that this whole thing has to be of size N, okay? In particular, what is this matrix in here? What do you do? Is the matrix contains as entries you take each data point, okay, the rows, you take them transpose, and then you multiply rows by columns, and these are just the scalar product of each input against each other inputs, okay? So this is what is called the Grimian Matrix, okay? And it's going to become a kernel matrix in, I don't remember, but soon enough. So this is size N by N, okay? And there is no X transpose here because I moved it before. So now the story is, and notice that here I rewrote it this way. See, look, I have W, X transpose times C. And of course, this I can rewrite like this. So this is exactly what we wanted. This line and this line are equivalent. Only here I'm specifying, here it was a hope. Here we proved it, and we showed, not only we show that it's true, but we also gave a rule to compute the coefficient Ci. So C here is just the vector with entry CIs given by the solution of that linear system. Again, it's just a linear system, okay? But what is the size of the matrix, n by n? How much does it cost us to solve that problem? Well, again, you have to form the matrix, okay? This is going to be vectors of size. How each row of these is of size d. And you have to multiply n of them against n of them. So this is going to be n squared d. Okay? And then you have to solve this. And roughly speaking, this is going to be an n cube operation at most. Okay? So again, we achieved exactly what we wanted, which is to swap in this new version of the algorithm the role of n and d. Okay? We got a dn squared n cube complexity. And so here you can play, okay? Depending on which one is bigger between n and d, you can solve the problem or another. Does that make sense? So this is exactly what we wanted to achieve. In the case of least squares, is really simple. By the way, also I realized yesterday I skipped that step, but it's also simple. It's just that you have to do a proof by induction. Typically, proof by induction always create a sense of discomfort for the first few seconds. But it's really one line too. Okay, so we're in a pretty good shape, okay? We introduced least squares. We did an amazing job of computing a gradient of the squared function. We set it equal to 0, we get a linear system. We also did an amazing computation here to show that the representative theorem holds, and now we have a W and C, and we're game. So what's next for us? We're still just restricted to linear models. So what we want to do next? Kernels, and we just take an intermediate step with nonlinear features first, okay? We say a finite number of nonlinear features. Do we really need to think about that after the whole fantastic lecture of yesterday? Well, I give you a bunch of linear features. What do? You take each input point, and you evaluate each nonlinear feature on the input point. And that's your new input point. Okay? And then you just say, oh, I was joking. X here is not really the data matrix. It's the, processed data matrix to the nonlinear features. But I'm generous, and I wrote it. Okay? So again, it's completely for free. Okay? It's, again, always have this, a bit of a schizophrenic perspective on this. You are a statistician and an optimizer, okay? So your optimizer side is happy because there's nothing you can do. You just add a pre-processing and you're done. As a statistician, you're very happy because you went from linear model to nonlinear models. And now you have wild function conditioned on the choice of phi. What about kernels? Well, again, we just proved that we have something like this. So all we need to do is to compute the C, and then basically go in this expression and replace the inner product with a kernel, okay? There is a lot of math hidden in what we did here, as I told you yesterday, but this is one genius idea that Vapnik had, just enucleate this one thing, call it kernel trick, hide all the math, and just teach people to do this thing. Whenever you see an inner product, turn on your math brain and just replace that with a kernel. And in fact, it kind of works. Whenever you do that, you can actually make a much fancier proof, which is a bit more rewarding, perhaps, but doesn't change the essence of the story. The final result is the same. So we're in a good shape. We can replace this. Basically, you can look at these two equations, and in one case, you will have to put the nonlinear features here, and in the other case, you will have to put the kernel. Okay? And now for each set of features and for each different kernels, up to the preprocessing and computing the kernels of the features, the computation of the algorithm is the same. More or less everybody at this point, if you stop believing all the lies I'm telling you for a second, everybody usually has at least one complaint about this whole story. After 2 days of, oh, you have a feature, how you have a kernel, and then you can do all these beautiful things. What is wrong in what I just said? Well, you don't have features, and you don't have kernels, okay? Sure, you have the Gaussian kernel, the polynomial kernel, but they're good enough for all your applications? No, they're not, okay? They're okay. they're surprisingly good, but they're not fantastic. So most of your time, whenever you have to solve a problem, is actually spent in trying to get and invent good kernels and good features, okay? For us, they're just a placeholder of one point where we can introduce something intelligent, but it's your intelligence, okay? This is just a mean. What I'm trying to say here is that this whole discussion starts from the assumption that you do have features or kernels, okay? More generally, you can think of this as some form of data representation. And if you want, grasping how to handle the problem of representing data is perhaps one or the biggest problem in machine learning still now, okay? There's a lot of good idea, but this makes a huge difference. It's fairly, acknowledged that once you have the right features, many different algorithms on top of it, logistic, SVM, least squared, this and that, are gonna perform similarly. Not the same, you still have to know how to use them, so this is, needed, you cannot jump this part, but having the right features is really important. It's amazing how many people there are extremely far. There is also... Okay, so the complaint that you didn't do, but I did to myself is, what about kernel and features? And the answer is, that's a huge gap in my discussion, and we're going to touch upon it the last day when we're going to discuss a bit of dictionary learning and a bit of deep learning, okay? Where these two aspects are somewhat tackled to some extent. But for now, today and even Thursday, we assume that we do have features, okay, of some kind, or kernels. Okay, so this is pretty much it for penalizing, Tikhonov regularization, or if you want, penalized regularization with least squares. There is a bit of name game here. The basic idea of considering things like wherever it is, this guy, it's often called Tikhonov regularization, but statisticians introduced the same idea exactly for this setting around the same time. This was the end of 60s, beginning of 70s, and it's often called ridge regression. Okay, and sometimes it's a fancier version are called kernel ridge regression or regularized least squares and so on and so forth. So what we want to do next is look a bit more carefully into this expression and understand something, okay? So we're going to do a little interlude. And again, imagine this stuff is more or less obvious to everybody, but let me just go slowly to it once, because we're going to develop this idea. What I want to do is essentially point out, highlight, an interplay between statistics and numerics, optimization, but really numerical analysis in this case, in fact, just linear algebra. So this slide has, for the time being, nothing to do with learning, okay? This is a generic matrix, a generic vector W, and a generic vector Y. And in fact, at the beginning, the matrix is not going to be generic. It's going to be an easy matrix. It's going to be a diagonal matrix, squared diagonal matrix, okay? So it's just a matrix, which is an identity, but on the diagonal, you have numbers, okay, different from 1. And they are ordered. The first number is big, the last number is small. Okay? You have to solve this linear system. What do? Well, you have to take the inverse of A and shove it to the other side. But this case is super easy, because this is just a diagonal matrix. So the inverse is just what? 1 over. Okay? So you see, what's the problem? Even in this case, it might go well and it might go wrong. When does it go wrong? Well, the eigenvalues in this case are literally just the values on the diagonal. And what he just said is, when any of those guys is 0, and I would also say, or very small, okay, very small with respect to 1, where for that, with respect to the biggest one, then you invert these matrices, and what might happen? If you perturb a little bit these eigenvalues, or you perturb a little bit Y, you might get a W, which is very far away. Right? Baby example, I'm assuming that everybody is almost at the stage of complaining about how easy this is. Well, let's go to a non-diagonal matrix. But let's say it's still symmetric and positive definite, because it will be enough for us. Well, in this case, it's not as easy, but almost. Because what you can do is that, I'm not saying to do this computationally, but just for understanding, what you can do is that you can diagonalize the matrix. You get U sigma U transpose. And when you have to take the inverse, so now you have the same game, okay? Solve this, but now A doesn't have this shape, it has this shape. So now you have to take the inverse. What do you need to do? Same as before on the eigenvalues, okay? So you have U transpose, but inside you take all the eigenvalues and you invert them, okay? The story is exactly the same as before, though. Nothing changed. If the eigenvalues are small, or even worse, 0, you might get that the matrix is either not invertible or unstable, in the sense that the condition number, the ratio between the two, is big, and this is a sign of instability. What does this have to do with learning? Well, this slide, nothing, right? If you look at this slide, there is no learning here. And this is just a slide out of a numerical analysis course, just plugged in the wrong place. But in fact, there is this interplay between stability and statistics, which is not so surprising. You know, a good statistical model should be something that you give me data, okay, and I handle them in such a way that I can extract some information that should not change that much if I change the data. Well, a good numerical algorithm should be something that gives me a solution that also should not change much, okay? A lot of details in what I just said are different, but at the high level, there is some commonality. And we don't want to dwell in the details or the philosophy of what I just said, but we just to merely exploit it, okay? So this is just what we just did, isn't it? We just took least squares, okay? And I'm going to be sloppy from the beginning, and I'm just going to assume that X transpose X is invertible, okay? If it's not, you have to put a pseudo-inverse everywhere, and nothing changes. But it's just going to make the notation heavier, okay? For those of you who are really bothered by this, you can do it yourself. Just put a dagger everywhere, and things are going to be just fine. But I'm just going to make it easy and assume that it's invertible. Which means that if you solve this problem, you're just going to have to solve this linear system, where X transpose X is just the data matrix. Now, if you could choose the data, you could choose them to be nice orthogonal, all nicely, you know, arranged in the space, but unfortunately you cannot. I can give you 2 points, which are just the same if I want, okay? Because I'm God giving you samples in a nasty way. So sometimes they're nice, sometimes they're not. Of course, if n is much smaller than d, for example, you will have that some of the eigenvalues will be different from 0. You will have to project. But even worse, you might have a lot of correlations between things, which is good, because it means that data are somewhat not so high-dimensional. But this, in turn, is going to tell you that your numerical problem is complicated. So we introduced this penalty as a way to avoid overfitting, okay? We didn't have any numerical aspect in mind. But if we now compare the solution to this and the solution to this, you'll see that, at least for least squares, I can give you a completely different story, which is I want to add the penalty because it's going to make my problem stable. Why? What did we do here? Well, let's go back to this slide 1 second. Assume that X transpose X was diagonal. What did we do? We took the diagonal, and we just added a little bit of thing on the diagonal. Why? Because if AD is small, now I just add a little lambda, and it kills it, okay? Which means that now my thing is completely invertible. In some sense, it says that the smallest eigenvalue is not going to be, so that the smallest value in the condition number is going to be governed by lambda rather than just the eigenvalues, okay? So the condition number of this matrix is just the biggest time divided by the smallest eigenvalue, whereas here you're going to have, roughly speaking, if the big eigenvalue is much bigger than lambda, you have still the bigger eigenvalue, but if the small eigenvalue is much smaller than lambda, you're going to have lambda. So you get A1 divided by lambda. Sorry, I call this sigma. Roughly, okay? Roughly speaking, if this should be small, And if it's much smaller than lambda n, we still get just lambda n, is negligible. And this should be big. So if it's much bigger than this, we roughly have this. This is just an approximation, but this just gives you a feeling, okay? So we are really curing the problem. We are going from bad condition number to good condition number. So the same thing, okay? We did this just one thing, and now we have two very complementary views to it. Overfitting, curing statistics, and numerics. Why do we care about this? Well, it's nice. You learn something, you have something you didn't expect, you find a connection. If you already knew it, you look at it again, you're like, yeah, it's still nice, okay? But you can also make it a bit more useful and say, there are people called numerical analysts that actually spend their whole life trying to make, this solution, to find ways to find stable solutions to problem. So maybe those are learning algorithms too, okay? Is that true? Well, it turns out to be true, in fact. Okay, and maybe we can generalize them later on. That's also true. So that is kind of nice. So suppose that you get this problem, okay? You might know nothing about learning, but you have to solve a linear system, and this is one way, okay? And remember, our problem is that some of the eigenvalues are close to 0 or even equal to 0. Suppose that you have to invent another way to find an approximate inverse of the matrix that is invertible, okay? So look what you did here. You took this and you replace it by this because its inverse is stable, it's nicer, okay? Think a second. Give me another way of doing the same thing in a different way. Let's do it here, okay? I want an approximate version of this. Let's do the diagonal case. How do you do that? What? Okay, yeah, so the pseudo-inverse, what is it doing? So it's just at the pseudo-inverse, okay? The pseudo-inverse basically says if the eigenvalue is 0, okay, is exactly 0, if here AD is 0, here, rather than writing minus 8d to the minus 1, you write 0, okay? So you throw it away. Is it good enough? It's a step in the right direction, but as I pointed out, maybe it's not enough. It might be that the small eigenvalues are small, and the pseudo-inverse only kills things that are exactly 0. So what is the other thing you can do? Truncate. Okay, what does it mean? That you decide what's small, and then you, in some sense, do the same thing you just did. So instead of just throwing away the eigenvalues that are 0, you throw away the eigenvalues that are small. What does it mean that you throw them away? Is that when you form the inverse, you don't write on the diagonal the ratio of the small eigenvalues, okay? Instead of writing 1 over something small, you decide what's small. Notice that you introduce a threshold, okay? Or if you want a dimension, how many you use, okay? There is a new parameter, which is what's small. Okay, either a threshold on the size of the eigenvalues or just a counting parameter. Let's do the counting parameter. Okay, they're ordered. So I take 10. I take the first 10, the first 20. So how do we do that? Well, it's very simple. Okay, maybe I called this U the slide before, but so you take x transpose x, you take its eigendecomposition. Then what you do is that you go on you form this matrix here, okay? This is more or less a placeholder for a notation. What is this? Well, you do the same thing you usually do when you form the inverse, but inside the diagonal, you don't put all the inverse of the eigenvalues, you just put m of these things, okay? What is the condition number of this? What is the condition number of the matrix that gave me this inverse? So the biggest eigenvalues is the same, okay, it didn't change. The smallest eigenvalue is now what? Well, the smallest eigenvalue different from 0, okay? It's sigma m, okay? So compared to that, okay? So here I had this divided by this. Now I have sigma 1 divided by sigma m. So we call this how do we call lambda? The regularization parameter. Where is the regularization parameter there? Is there a regularization parameter? Where is it? Let's take votes. Do you see a regularization parameter here? Who says yes? Who says no? Well, it depends how strict you want to be in what you call a regularization parameter. If regularization parameter is the thing that you write as lambda or gamma and sits in front of the penalty, there is no regularization parameter. If you call a regularization parameter something that controls how stable is my algorithm, and in a minute is going to control overfitting and oversmoothing, then yes, there is one. Because M, if you're lucky, is going to do exactly that. Okay? And in fact, it is exactly true. What you can see is that M and lambda are doing in a different way exactly the same, implementing exactly the same principle. And this here is just another learning algorithm, okay? In numerics, this is called truncated singular value decomposition or spectral cutoff regularization. In statistics, this is called principal component regression, okay? Why is that? Well, we're not going to cover this, but again, this is not your first learning course, and I hope that in your first learning course, somebody taught you what is a PCA, the principal component analysis, okay? You know it very well. He's one of my students. So, Giovanni, do you know it? What is principal component analysis? Well, there are many ways of seeing it, but the basic idea is I give you the data, the unsupervised data, okay, the matrix of the x's, okay, and then you would like to know if there are directions where the data are particularly elongated, where they move a lot, okay, where there is a lot of variance. And then I want to know which are these directions. So I take the first biggest direction, then the one orthogonal to it, and keep on going, and try to basically discover what are the dimensions of the space that matters the most. Right? You can think in terms of geometry, taking the projection of the data that keep most of the information. You can take a probabilistic perspective where you talk about variance. But how do you do it computationally? Anybody remember? Assume that is written behind me, for example. You take the matrix of the data, you form the X transpose X. This is up to a centering of the data. It's what you call the covariance matrix or correlation matrix. You should recenter data, okay? So we are sloppy about that. And then what you do is that you take its eigenvalues and eigenvectors, okay? And you order the eigenvalues, and you have that the biggest eigenvalue is going to be exactly giving you this dimension, and the second biggest, the other one, and so on and so forth, okay? This smells a lot like what we just did, because what we just did was taking just the first M of this and inverting this matrix. So what are we really doing? Well, it takes, again, a couple of lines to show that this algorithm that we just view as a way to do numerics, okay, in an alternative way, can be interpreted as follows. Take your data, okay, perform PCA. Do PCA on the data. It means that if they were dimension D, again, PCA is a dimensionality reduction technique, okay? So if you have the data which are n times D, they becomes n times m. Okay, you project them down. Then what you do is that you just do least squares with no penalty. Okay? That's it. So you take the data, which is n by d, you map it into a new matrix, which is n by m. This is the projected matrix. Each point is projected on the first m eigenvector. And then you solve, let me put m here to emphasize that it depends on m dimensions. Then you solve this problem. Okay? It looks the same as the one that I just showed you, but here you have this new matrix, and here you have a new vector. Okay? You can prove that basically this is equivalent to the TSVD I just showed you before. It doesn't take a lot. It's basically an exercise. But I think we even published a paper on this at some point. Okay? Why? Well, because I kind of find it interesting that you learn that PCA and then a learning algorithm with no penalization and no regularization is already regularization. PCA plus risk minimization is regularization, okay? In the sense of stability. And this is just, I'm just playing the game of making the analogy with the ridge regression. But you can prove it. You can prove, you know, tell me whatever definition you want of regularization and any theorem you want. You can prove it for this guy too. So this is regularization in a very precise sense. Why is this instructive? Well, because PCA and dimensionality reduction in general are one of the most common pre-processing of data. Okay, and this is basically telling you, be careful, because if you do dimensionality reduction and then you just do error minimization on supervised data, this might be already enough. So suppose that you don't know this, okay? Suppose that you've never seen this. Then the thing that you would typically do is say, oh, I do PCA, and then I still have to learn. So I'm going to add this guy. Okay? You could do that, right? But what happens? You're doing the same thing twice. You're doing it here, and you're doing it here. M and lambda plays the same role. You're just doing the same thing twice. You might want to do that, but you have to be aware that you're doing it. So this tells us two things. First, projection regularizes. Dimensionality reduction regularizes. This is one instance. It's the one instance where you can prove it. For PCA, you can prove it also for other loss functions. I think it's a project to show how that this is true for all the others dimensionality reduction problems. Empirically, you see it immediately, okay? You take any dimensionality reduction technique you like, unsupervised, couple it with the supervised objective, you can prove that it's doing regularization. But strictly speaking, I know how to prove it for PCA, okay? So dimensionality reduction regularizes, so be aware that when you couple dimensionality reduction to a supervised learning algorithm, you might be doing the same thing twice, okay? So that's why I think this thing is interesting. And of course, you see why it's called principal component regression, okay? And it also tells you something bad about ridge regression. What ridge regression is doing is taking basically, it works when the W I'm looking for depends on the first few principal components of my data, okay? Because here I'm basically saying, throw away the small eigenvalues, which means throw away the small principal components, okay? TSVD, throw them away. Ridge regression, you know, downplay the role, okay? But it's kind of the same idea, okay? So this is the first big kind of class of regularization I wanted to show you, which is not penalization, okay? And maybe you can sweat and turn it into penalization, but do you need to do that, okay? Is that important? Or is this enough for you? Well, it depends who you are. If you're really in love with Tikhonov regularization, then you should play the game. For me, this is good enough. Now, what are we left to do here? Well, the same game, but we're not going to do it. What if, instead of linear models, you want to use nonlinear features? You take the data, you map them through the nonlinear features, you get the new matrix, and you do the same thing. What about kernels? That's going to take a little more, and we're not going to do it because we don't have time. But the basic idea is that, so this is just a change of notation. I call x hat phi hat. But with PCA, it takes a little more. But long story short, the algorithm is easy. Proving that this is equivalent to the one before takes a couple of lines. But essentially, you're going to have the same expression as before. And then you have a similar expression for the C. But rather than the data matrix, you have to take the kernel matrix, invert it, and truncate. Okay? Or rather, truncate and invert it. Okay? So it's not too hard to prove this, but again, we don't really have time. It's just a linear algebra trick, and it takes a few lines, okay? But it's exactly what you get. So this is kind of what you hope for, okay? If I didn't show you this slide, and I thought, what do you hope for to get when you do nonlinear features and kernels? When in one case, you want to get the data in the new features, in the other case, you hope that you can just get that expression over there. And you can compare that expression to what you get for ridge regression, which is this, right? So it's yet another way to do the approximate inverse, in this case of K. You would like to do, this is an approximation of K dagger, and another one is KM to the -1. Okay, so it kind of fits together nicely with everything we saw before. Wake up. Okay. Any questions about this part? How many of you saw principal component regression in your life before? And you cannot. 2. All right. So it's really kind of the same as Tikhonov, okay? And you can extend it with kernels, and it's actually a pretty useful algorithm. How much does it cost us computationally? What do you need to do? What is the main computation you need to do to compute PCA? An SVD, okay? So it's roughly the same as Tikhonov, okay? It might be a bit less if you have to compute only few eigenvalues and eigenvectors, but it's roughly the same. All right, so the one we want to show next is one of my favorite ones. It's one of my pet projects. I've been doing it for quite a few years, and I think it's one idea that is becoming more and more useful as we're dealing with bigger data sets, okay? And it's the idea of early stopping. So do you know what's early stopping? Anybody? You don't count. Giovannino? Giovannino, you don't know anything, I mean. So early stopping is probably one of the oldest tricks in neural networks, okay? The idea is that you train, okay? You do some black magic somewhere that you don't know, but then you train, and then you look at the test error, okay? You train and optimize the empirical error, but at the same time, you keep some data on the side, sometimes, and you look as the iteration proceed, as the way the error evolve. And typically, it goes down for a while. The empirical error keeps on going down because you're optimizing it, but then at some point, the test error goes up, okay? The validation error goes up, and then you stop. Easy enough, right? Why does this make the slightest sense, and how is this related with ridge regression, okay? It makes a lot of sense. It's kind of nice. Imagine it. You have this one parameter, you run it, you monitor this curve going down, 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 and boom, then you stop. If you're lucky, maybe you stop very soon, and you don't have any computation. Compare this, for example, when you solve logistic regression, okay? What you have to do is that you have to take the iteration and run it all the way down to convergence when the empirical risk is 0. Here we are saying we don't have to go where the empirical risk is 0. At some point, we stop and go away, okay? What this has to do with ridge regression? Well, the spoiler is that if you're using the square law, this is essentially equivalent to ridge regression, okay? And that's what we want to show next. So here is the idea. The algorithm is easy, okay? It's exactly the gradient descent for least squares. It looks a little bit for what we did with logistic regression, but what is the main difference up there? When we did logistic regression, we added a penalty, okay? Whereas there's nothing, okay? So what are the free parameters in that algorithm? This is always a good question. I give you an algorithm, and I tell you, oh, this is an algorithm. And you tell me, well, what are the free parameters, and how do I choose them, okay? If you don't tell me how do I choose them, it's just a half algorithm. So let's begin with the first question. How many free parameters you have in this algorithm? It's not super hard because you have to list the symbol and say, I know it, I don't know it. How many symbols you have, okay? How many parameters you have? 1 or 2? Which one? Gamma, okay? And the number of iterations, okay? How many times you do it. So you have 2 parameters. That's the only thing, you know, once you know that, you show that you can just use it, okay? What I'm going to show you next is that you can choose gamma once and for all in a universal way, depending on the data, but the iteration is going to be a regularization parameter, okay? And we're first going to show it in a kind of intuitive way, and then we're going to prove it in a slightly more principled way. So this is the intuitive way. So allow me to write something down that assume that we are not working with the linear model, but rather with nonlinear features, okay? This gives me a bit more, I want to show something in one dimension, so I need to give myself a bit of power. So suppose that you run gradient descent. You're using a basis, say, of sine and cosine on this one-dimensional problem, okay? So this is x, this is y, this is just a bunch of points. You run gradient descent, and you start to optimize. You start from 0. At the beginning, you have a simple solution. And now you take more steps. What do you think is going to happen? This red curve is going to look more like what? It's going to start to get closer to the data, because you're trying to make the error smaller, right? So it's going to go up, it's going to go up. By the way, it's an amazing thing that Rafa did is almost a movie, almost. So at some point, it's going to get wiggly, okay? And if you let it go enough, it's going to pass through. If you give enough features, it's going to go through all the data. You like them all. You want to make the errors small for all of them, okay? But if you look at all these curves, which one looks the best to you? This one, this one. So 1, 2, 3, 4. 3 kind of look good, okay? 3 or 2, maybe. Well, no, 2 is too flat. This one kind of look good. This one kind of look like it's feeling the right gist of the data, but it doesn't fall in love with the particularities of your data set, okay? So you just did early stopping in your head, right? You look at this curve and you decide that somewhere along the line of the iteration, you don't want to go all the way down. Why? Because you're not trying to make the error on the data small. You kind of know that you want to predict well future data. And future data are not, they don't care about the noise, okay? They care about trying to get the right shape of the true function. Again, the difference here is in optimizing the empirical risk, which is what you can do, versus optimizing the expected risk, which is what you want to do. If you look at the empirical risk, the training error, as a function of iteration, it goes down for a while, and then it keeps on going down for a while. But if you look at the test error, it's going to go down for a while, and then up. And if you want, from a pragmatic perspective, this is a visual proof of that, okay? You're basically saying, yeah, of course, because I'm fitting. At the beginning, I'm over-smoothing, and at some point, I'm over-fitting if I fit my data, okay? Of course, you give me 3 features, and I might be able to do it. But if I have enough room, then I'm just going to do the job, okay? So this is convincing enough. So already with this, you'll see, I'm going to give you one explanation of why this is true, which holds for the least squares. But in fact, you can convince yourself from this plot that this is probably going to hold for all other loss functions, right? Because it's such a basic idea. And in fact, you can prove that this is indeed true for all the loss functions we have seen. So how do we prove that this is basically Tikhonov, okay? It cost us a couple of reasoning, okay? What I want to show you next, in the next few slides, is that when we run this iteration, in fact, we are exactly doing something like this. Something like replacing an inverse with an approximate inverse, okay? The question is, which approximate inverse are we using now? Does it make sense? This is the question we want to do next. How do we do that? Well, we have to take a couple of steps, okay? In fact, one step that, as usual, we're going to skip, and then introduce the mathematical effect. I imagine if I didn't make any typos, I did one, because this I did just before coming here. It's clear that you can rewrite this expression like this, right? And what you can convince yourself, if you write the first iteration, the second iteration, the third iteration, and you look at it, is that by induction, you can prove that if you want to write down the iteration number t, okay, you can write it in closed form this way. Okay? So if you take this expression, for iteration 1, 2, 3, or if you just prove by induction, okay, you can prove that the iteration number t can be written as a certain sum of matrices elevated to some power applied to x transpose y. Okay? Now we stare at this. Is this statement clear? I'm saying that wt, after t steps, can be written in closed form this way. This is going to be useful in a minute, but let's just see a reason why it might not be useful, okay? From a computational perspective, this is very nice. What is the cost of this? Well, you have to do matrix vector, which is nd, then you have to do it again, which is again nd, so it's just nd times the number of iterations. Okay? So this is NDT. So if you can do not many iterations, this is at least an order of magnitude smaller than the other algorithm we have seen so far. If you have, this is another way to compute the same thing, okay? WT can be written in two ways. One requires a recursion, one just write down a closed form. But if you check how much it costs to compute this, this is cubic, it's bigger, okay? So we don't want to compute this. We want to compute this, but this is useful, okay? Because these start to look a little bit, this is just a power series of matrices, okay? So that's what we want to look at. This is going to be interesting for interpretation. So let's look at this a little bit more, okay? Suppose for a second that instead of gamma x transpose x, I just have a real number. I call it A, okay? Then again, if I didn't make any typo, what you have is that if you take a power series, j from 0 to infinity of aj, and a is smaller than 1, what do you get? This series converges, is the geometric series, and it converges to 1 minus a to the minus 1. Right? Now you can change variables, and you can write here 1 minus a and here a. Maybe I should have called it b, okay? Does this make sense? So if you have a number to the minus 1, you can write it as an infinite series, okay, of 1 minus a to the j. Okay? So what we want to do next? First of all, we actually discover that that equation holds if A is a matrix. Okay? And then when we compare this expression to this one, we just saw that this goes to infinity, where that has a truncation inside. So the first thing is exactly the extension of this result to matrices. And again, here I'm sloppy, assuming that things are invertible, that everything works in any case. So what you have here is that rather than the real number to be smaller than 1, you have to assume that the biggest eigenvalue is smaller than 1. And then what you have is that this series of matrices converges, okay? And it converges exactly to a to the minus 1 if I take infinitely many of them, okay? So it's just the power expansion of an inverse. Do you see where I'm going now? We're basically going to apply this result using, in place of A, x transpose x. And then we're just going to say that rather than go all the way down, we truncate. So x transpose x is equal to this thing here. And then what we do is that we truncate. So two observations. Why do we need gamma in that expression? How do you choose gamma? What is a good choice of gamma? How do you choose gamma? Well, sorry? Exactly. Okay. So we need here the number to be smaller than 1. Okay. And in fact, these are just positive numbers. Here we need the norm to be smaller than 1. Okay. Otherwise, this doesn't converge. This doesn't converge. Okay. Here, x transpose x might not have an eigenvalue smaller than 1, right? It's just the data. So what you need to do is to put a gamma that makes it small enough. Okay, smaller than 1. This is the choice I skipped at the beginning. Okay, so that's why you use that. So gamma doesn't play, at least in this formulation, the role of a regularization parameter. It just is a constant, okay? There is a good choice that doesn't depend on how complex is the problem, okay? But T here really controls the degrees of approximation. You can compare to this. Here lambda controls how well I approximate. Here T controls how well I approximate my inversion. And you can convince yourself that, again, here the condition number depends on T. In some sense, intuitively, we're not going to write it down explicitly, but intuitively what you see is that the effect of truncating this series is much more dramatic on small eigenvalues. So the biggest eigenvalues are basically going to stay unchanged, okay? Whereas the small eigenvalue are going to essentially be killed by this truncation. To understand that, basically you have to think of this, where A is each eigenvalue. And what you see is that when A is close to 1, truncation doesn't really do much, but when A is close to 0, truncation essentially kills everything. Okay? Does it make sense? So, if you're happy enough with this plot, this is one way to understand early stopping. But for ridge regression, we can actually make a precise connection, which essentially hinges on an extension of a usual series, which is the geometric series, two matrices, the so-called Neumann series. Okay? So this is it. Okay? Few comments. So any questions about this? That makes sense? Did you see what we're doing here? So again, first we just show a numerical example where you see what's going on when you do early stopping. And then what you see is why, at least in the case of least squares, doing early stopping is actually a very principal way to find the matrix inversion by essentially doing a truncation of a series expansion. Okay? So these three algorithms I show you are a family of what is sometimes called spectral regularization or spectral filtering, because basically they are all very similar in a way. In which sense? They have something very similar and something very different. What's similar and what's different? I'm not sure that staring at the equation is going to help you a lot. You're deflecting me, but I'm not sure it's going to help a lot. So what do I have in common? They kind of look all the same in a way. Okay? In which way? All of them say, take an inverse and replace it with something else, which is a stable approximation of that inverse. Okay? Take an inverse that might be unstable, because the eigenvalues are not nice, and then take another one, which is nicer than this. So in that sense, if I use this level of precision, these three things are doing exactly the same thing. Okay? Why do we call them spectral filtering? Well, the standard way, the most classical example of a filter is what? You take, the low-pass filter, I guess, is the most famous one, right? You take a signal, you write it down in some harmonics using Fourier basis or Fourier series, and then you keep only the slow frequencies, okay? And if something is oscillating a lot, you cut. Do the analogy here, okay? Instead of high frequencies, use big eigenvalues. Sorry, instead of small frequencies, slow frequencies, you use big eigenvalues. And instead of high frequencies, you use small eigenvalues. Then you're doing the same. You're basically saying, I order my eigenvalues, okay? And then I have a window of some kind that cuts the small ones. You can view them as the higher order information. So when you have harmonics, you think of slow frequencies as the first order information, and then you have higher order information, which is the high frequency. Here is the same. These big eigenvalues are the big principal components, are kind of the first order information about your data, and then you have the small eigenvalues, which are kind of the second order. And we're saying we want to kill them. So that's why you can see them as spectral filtering, okay? And in some sense, you can, well, in some sense that you can make precise, you can see each of these algorithms as the choice of a low pass, okay? Something that kills small frequencies. So this is what's similar, and in fact, you could even abstract these ideas and introduce other algorithms that are basically just, you can think of other windows, okay, and see if you can make it faster. For example, what you can see is that there are a bunch of methods that can be written this way, and it can all be analyzed in the same framework, because they're all ways to basically throw away small eigenvalues. So in that sense, they're all the same. Yep. Or big eigenvalues, to be more precise. So what he's just saying, which is exactly true, and I said it, but it's worth remarking, is we're discovering that least squares somewhat put all its money on the big eigenvalues. it's not a big discovery, right? Because if you just look at this equation, it's obvious. But this makes it even more explicit. And so all these algorithms that I show here do exactly that. And notice that sometimes the only caveat is in the linear case, this is the principal components of the data. If you use nonlinear features or kernels, these are not the principal component in the data space, but they are the principal component after you map the data in this new space, okay? So they are the kernel principal component on some form of nonlinear principal component. So it's a bit more complicated, but this gives you a feeling of what's going on. Absolutely. So this is what's similar in all these algorithms. They all rely on the same assumption, and they all implement it in a slightly different way. What's different? Well, if the way you implement these guys is by first taking the eigenvalue decomposition of the matrix and then just doing something on the eigenvalues, nothing. But if you remember the way we started, we don't do this. We actually do this, okay? And the complexity of this could be so much better than the other ones, okay? What you have here is that you have nd squared d cube. Here you have n dt, okay? Where t is the number of iteration. How many iteration you need? I don't know. You don't know either, okay? You can prove that square root of n is good enough, but you can essentially check in application, this might be very small. If your data, the sooner you overfit, you stop, okay? So if you have a powerful enough model, what you're gonna do is that you're gonna start to optimize, and then you go out. So t can be much smaller both than n and d. Not only that, we're not gonna show it here, but one question you can ask is, well, gradient descent is the dumbest iterative methods I can think of. I can use better ones. I can use faster ones, okay? Does the speed of convergence give me anything, okay? Suppose that I give you a way. So remember this plot, okay? This plot says for gradient descent. Then I come to you and say, look, with my friends, we're amazing optimization people, and we invented a fantastic algorithm to optimize, very similar to gradient descent, but much faster. Is it good or bad? Can we use it or not? Is the question clear? So you have gradient descent, you know everything now, you have the whole theory. But now I come to you with something that is much faster than gradient descent. In doing what? In optimizing the training error, right? Because that's what gradient descent does. Can we use it? What's going to happen? So if this is the plot for gradient descent, how hopefully will the plot for an accelerated gradient descent will look like? Well, the training error is easy, okay? Instead of that training error, we'll have another training error that goes how? It goes down faster, okay? So this goes down like this. You're going to have another one that goes down much faster. Do we care? Not so much. What about the test error? What's your hope? That it's going to have the same shape, maybe, roughly, but it's going to be happening before, okay? So because the idea is that here is overfitting, but if this goes down much faster, maybe overfit, this level is going to be reached here. So the tester is going to go down and then up, okay? Which means that you can stop before. Indeed, it can be proved that there are algorithms where here, rather than t, you can put square root of t. So you can get the same precision with a square root of the number of iterations, the order of magnitude faster, potentially, okay? So a couple of comments. First, there is a big difference between Tikhonov and the other two methods in that Tikhonov is a continuous regularization method in the sense that lambda is a real number, where the other two have just discrete regularization parameters. So one thing you can ask if this kills you to some extent. Well, asymptotically, it doesn't, okay? And in practice, you almost never see that everything is happening between iteration 1 and 2. Okay, this happens for a bunch of reasons, because you can choose the step size, but also in practice because in our case you always choose the kernel or the features, and so you always have two knobs to turn. okay? So the concern that discretization of the regression parameter is going to kill you, I've never seen it. What do you gain? Well, we already saw that if you know where to stop, you can get fewer iteration. But what you really gain is an insight, very important in practice, related to what is called the regularization path. Do you know what's the regularization path of a learning algorithm? Anybody? Zero. It's important. It's a good. It's an important concept. Suppose that I give you, say, logistic regression or SVM. Okay, there is lambda, the regularization parameter. You have to choose it. What do? You try many values of lambda. You compute the solution for many values of lambda, and then you do some cross-validation black magic or some other black magic, okay? So the black magic part is not, as you might have understood, is not the topic of this course. But what we care about is the computation. So you have to run, think what you do with logistic regression. You fix lambda, and you run it all the way down to convergence. Then you fix another lambda, and you go all the way down to convergence. Of course, here you can play tricks, because you can use the solution you compute for one case to restart the solution you have to compute for another case. But still, you have to do this operation for many values of lambda, right? A regularization path is a set of solution of a learning algorithm indexed over the regularization parameter, okay? Is the path of solution you get for different values, for example, of lambda, in the case of penalized. What is the path of an iterative method? Well, the regression parameter is just the number of iteration, steps, okay? So it means that it's exactly the minimization, okay? So this is the regularization path. But this means that in iterative methods, the regularization path is built in the way you solve the problem. You don't have to think. For example, for SVM, there has been a bunch of literature on how, if you have a solution of an SVM for one lambda, how you can update and get the solution for another lambda. And you have to think about that, okay? So how do you do that? How do you go from one solution to another solution to another solution? There has been a few papers studying this problem for SVM. Here, you don't have to study it. For iterative methods, it's for free, okay? There is a natural warm restart property. You get one solution, then you compute the next one over, you compute the next one over, and keep on going, okay? If you imagine that you have a lot of data, this turns out to be very useful, okay? And in fact, if you look at good practice in large-scale application, early stopping is often mentioned one of those to use. Of course, you know, you can discretize, there are situations where maybe you can discretize lambda in a good way, you can do it at a good scale, but that's an open problem. How to do that search of lambda in a good way is something that we don't really know how to do well. And so iterative regularization provides a simple solution, okay? And this is more or less it for the meat. Again, we don't spend much time on going beyond linear models because, again, it's the same game as before. If you do go to nonlinear features, it's straightforward, okay? If you go to kernels, this takes a little more, okay? This takes a little more to prove it, but again, the algorithm is super easy. It's just the iteration of the C vector coefficients just with this term here. Well, this is just, again, the kernel matrix. And again, this is n square t, okay, compared to the n cube that you have to pay if you just do kernel ridge regression. So this t is small, this can be order of magnitudes faster. Also things that if you have to do n cube many times for different lambdas, this is going to kill you even more. So what about other loss functions? So clearly here, there's something that depends on the loss function, something that doesn't depend on the loss function, okay? What depends on the loss function here is my derivation, is the connection to Tikhonov regularization, because I do it through linear algebra. The linear algebra I use, the power series, the truncated of the eigenvalues, really depends on the fact that I'm using least squares. But clearly you can ask, what if I do PCA plus empirical risk minimization for other loss functions? You can use it, you can do it, okay? And it has been done at least for the hinge loss function. You can do it pretty much for all of them. And again, one question will be, what if I don't use PCA? I do Laplacian Laplacian eigenmaps or isomap and ERM. Does it work? I think this is a project. It's not done yet. But I'm also betting that you can try this afternoon and it works. What about other loss function for early stopping? Well, here there are two directions, okay? So for other loss functions, you can prove that it does work, okay? And we've been doing it recently in a couple of papers. But this is just the beginning, because again, this is a new way to look at optimization, okay? You can open the book of all the optimization algorithms and say, okay, these are optimization for the training error, but what about the test error, okay? So you can try to see if the improvement you see on the training error translate, and how complicated it is to prove it, that they translate to test error performance and early stopping, better early stopping criterions. So, what time is it? 6 minutes. Grand. So kernel methods were the algorithm of choice in the late 90s and early 2000s. In the last few years, they're still used, but they're not the algorithm of choice, largely because what happened in the last 10 years is that we got big data sets, okay? So 10 years ago, one would have entered this picture and say, yeah, you know, the problem of life is that you never have enough data, so you have a blah, 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 blah. But now, unfortunately, we do have enough data. Or let's say, I'm not sure they're enough, but they're enough to kill my laptop and most people's laptop, okay? Because they don't sit in our memory, okay? The problem is not speed as much as memory. The methods we show you in this most powerful version, the kernel version, requires storing or at least computing the kernel matrix, which is size n by n. And this is too big to do anything useful. Okay? So in the last few years, well, too big to be anything useful means because you cannot put it into the computer. Suppose that you have 1,000,000 points, it's going to be 1,000,000 by 1,000,000 matrix. If you just do a back of the envelope compilation, you just see that it doesn't stay in most of the RAMs. Okay? And you can keep on buying bigger ones, but they're very expensive, and after a while you run out of, you know, it grows quadratically, so it gets very expensive and it stops pretty soon. So what do we do? So people have been thinking of ways to improve in this, and there are a few ways, okay? The first idea is, well, let's go backwards, okay? I give you a kernel, and then you spend time to try to find a feature map that approximates this kernel. Because you know that in that point is the size of the feature map that governs the complexity of the problem. You go backwards. We said we want to go from features to kernel, and I say, ah, they're too big, let's go back to features, okay? And there are a bunch of ways of doing it. You can try to engineer them, but there are ways of basically saying, I give you a kernel, can you give me an approximate feature, okay? The classical example is the Gaussian kernel that can be written as a list of sine and cosines, okay? In effect, just cosine is enough. This is what is called random features. So aside from the details of how you do this, which is going to take me a bit more than the time I have, the basic idea is, again, to go backwards. You cannot say, if I give a kernel, can you give me an approximate feature map, maybe finite dimensional, because I might not find an infinite dimensional one, but that I can exploit to reduce my computations. This is the random features approach. Another approach is subsampling, okay? The idea here is, remember that we have these representer theorems that tell us that our solution looks like this. It's a linear combination of the training set, the kernels centered at the training set points. Okay? So what if, inside the training set points, I choose only m of them? Be careful. I'm not throwing away data, okay? I have n points. I choose m of them to represent my function. Here. So my functions are going to be written as a linear combination of m coefficients. We're almost done, because you're almost killing me. But you're going to use all the data to compute these coefficients, okay? Is it clear? This is super important. I'm not throwing away data. I'm using m coefficients based on subsampling m points in the training set, but I'm still using the whole data set to estimate this coefficient. You can prove that in this case, rather than the full kernel matrix, which is n by n, you need the n by m, okay? You need all the training set points, but you need only m inner products. This is the other method. The other ways is to go back to the 80s and say, forget about that. What I'm going to do is that I'm going to use this idea kind of, but rather than sampling the points from the training set, I'm actually going to try to optimize the location of these guys. How? Well, for example, I first optimize over this, then optimize over this, then optimize over this, then optimize over there, and I keep on going. Unlike the first two techniques I showed you, where you can prove pretty much everything, these techniques you can prove pretty much nothing, okay? But as you can imagine, if you can make it work, it's not an unreasonable idea. You're just trying to be greedy, okay? And this is essentially what neural networks are doing. And then, of course, they can repeat this in many layers. So this is a one-layer neural network. The main difference is that rather than fixing these guys, you optimize both. So the beauty of fixing or randomly sampling this is that the dependence on CI is nice, is linear, okay? And so you always get, or most of the time you get convex optimization. The dependence on the Xis is complicated, is hidden in the kernel, or some nonlinearity, and it's typically complicated, and that's what makes the problem not convex and messy to solve in practice. And we're done. So again, the main scope of this class was to open up your mind beyond penalization, okay, and realize that when you do things like dimensionality reduction or projection techniques, you're actually going beyond penalization and still doing a form of regularization. And then show that there is another way of doing it, which is important again, which is just take an iteration to solve an empirical problem, which is noisy, and then stop it, okay? So what we want to do next, and next is in half an hour, is to move beyond the simple supervised learning we've seen so far into the realm of when you have more than one problem to solve, and you hope that you can solve them better by tackling them all together. Okay? Any questions? Otherwise, I propose to go for coffee and ask me questions in a separate moment.